Have you ever wondered why molecules take on such specific, recognizable shapes instead of just clumping together into random piles? It happens because of a simple mechanical rule. Electron pairs naturally repel each other. Think of them like roommates in a small apartment who want to stay as far away from each other as physically possible. Methane is the perfect place to see this rule in action. It's the gas that bubbles up from the mud and swamps, and the main ingredient in the natural gas we use for fuel. The physical shape of this molecule is entirely determined by the way its electron pairs divide up the space around the center atom. In methane, the central carbon atom has 4 pairs of electrons, and all 4 are busy holding on to hydrogen atoms. Because those 4 pairs push away from each other with equal force, they form a perfectly symmetrical pyramid. We call this a tetrahedral geometry. If you measure the angle between these bonds, it's exactly 109.5 degrees. This represents the maximum possible distance 4 items can maintain from a center point. When every electron pair is bonded to an atom, the molecule reaches a state of total symmetry with that baseline 109.5 degree angle. Now, consider ammonia. You'll recognize it by that sharp, stinging smell in heavy-duty cleaning products. It's made of 1 nitrogen atom and 3 hydrogens. Nitrogen also has 4 electron pairs, but only 3 are holding on to atoms. That 4th pair is left over, sitting on top of the nitrogen atom as a non-bonding pair. Here is the golden rule. Because that non-bonding cloud is only attached to 1 atom, it takes up more space and acts like an invisible hand pushing the other bonds down. This pressure squeezes the angle from 109.5 degrees down to just 107. Since we've lost 1 corner of that original tetrahedron, we call this new, squashed shape a pyramidal geometry. Perfect symmetry is broken the moment a non-bonding pair is involved, proving that empty electrons still exert physical force on the molecule. This effect gets even stronger in a water molecule. Oxygen has 2 hydrogen bonds, but 2 leftover electron pairs. The mechanical logic is simple. If 1 leftover pair pushed hard, 2 leftover pairs push twice as hard. This double squeeze forces the bonds into a sharp V shape. The angle collapses even further, landing at exactly 104.5 degrees. This is an angular geometry. Water is more bent than ammonia because every additional non-bonding pair acts as another hand squeezing those angles tighter. For our final shape, look at carbon dioxide, the gas we exhale. In molecular geometry, a double bond behaves just like a single one. The central carbon atom here is attached to 2 oxygens, and it has no leftover electron pairs. Without any invisible clouds pushing from above, the 2 sides repel each other equally and stretch out into a perfectly flat 180-degree line. This is a linear geometry. When there are no non-bonding pairs to interfere, a molecule will always take the straightest path to stay out of its own way. Remember the sequence of the squeeze. Methane is at 109.5, ammonia drops to 107, and water closes to 104.5. These 4 shapes all come from the same law. Electron pairs repel each other, and the ones that don't bond exert the most pressure. This rule is incredibly accurate for small molecules, and it serves as the building block for understanding the much larger, complex structures that make up our world. This leads to a mystery we'll solve in the next lesson. If geometry is so consistent, why do 2 things made of the exact same carbon behave so differently? Why does one scratch glass while the other dissolves on paper? These microscopic angles are what ultimately define the physical properties of everything we touch.